Florida has not seen drought like this in 25 years. Not a dry spell, not a slow season. Nearly 80% of the state is now classified as extreme drought, the second worst category on the scale, and the ground is cracking open in places that were underwater during last year's hurricane season. But Florida is almost a footnote in this story. Alabama is 100% in drought. Georgia and South Carolina are in the mid-90s. More than 60% of the contiguous United States is now in moderate drought or worse. The Southeast, which is supposed to be one of the wettest regions in North America, dried out faster than almost anyone predicted. And a major new study published in April suggests the machinery driving that drying may be something far larger than a regional weather pattern. To understand what is actually happening here, you need two things. First, the immediate cause, the weather system that locked rainfall out of the Southeast this spring. Second, the deeper signal, what an ocean current running 3,000 miles away might have to do with rain falling or not falling on American soil. Start with the Bermuda High. It is a semi-permanent high-pressure system that sits over the western Atlantic, and it has been running unusually strong and unusually far west since late winter. High-pressure systems rotate clockwise in the northern hemisphere. When the Bermuda High parks itself close to the coast, that rotation funnels Atlantic moisture up the eastern seaboard and into New England, and simultaneously pulls dry air down from the interior of the continent into the southeast. The rain goes north. The drought goes south. That mechanism is not new. What is new is the persistence. Normally, the Bermuda High wobbles and retreats. Storm tracks shift. The pattern breaks. This spring, it did not break. Week after week, the same ridge held, the same dry air subsided over Georgia and Alabama and Florida, and the soil moisture deficit compounded. Drought does not announce itself the day it starts. It is a slow debt, and by the time the balance comes due, the landscape has already changed. In Florida, the consequences arrived fast. Wildfire risk across the northern part of the state jumped to critical by March. Lake levels in the Central Lake District dropped to multi-year lows. Agricultural losses in strawberry and citrus production, already battered by years of disease pressure and freezes, pushed into the hundreds of millions. Water management districts issued restrictions weeks earlier than typical drought years. In Alabama, where drought is now total and statewide, row crop farmers planted into powder. Pastures that should have been greening in April were brown and brittle. Reservoir levels across the Tennessee Valley fell. And in Georgia, cities that spent the last decade upgrading water infrastructure after the historic 2007 drought started, watching their gauges again with the kind of attention that means something is wrong. The speed of the expansion is what set off alarms among climate scientists. Drought footprints can grow fast when conditions are right, but this one moved across a multi-state region in a matter of weeks. The U.S. Drought Monitor, which runs on weekly updates, was being outpaced. Categories were jumping by 2 levels in a single reporting cycle. The technical term for this is flash drought, a rapid onset event driven by heat, low humidity, and persistent high pressure that consumes soil moisture before monitoring systems can fully track it. Flash drought is not new either, but its frequency is increasing. And that is where the second part of the story begins, because increased frequency of anomalous, persistent, high-pressure events over the Atlantic may not be random variation. It may be a signal from the ocean itself. The Atlantic Meridional Overturning Circulation, AMOC, is one of the most consequential physical systems on the planet. It is a massive conveyor of water. Warm, salty, buoyant water flows north along the surface, from the tropics toward the North Atlantic, releases its heat into the atmosphere, becomes cold and dense, sinks, and returns southward along the ocean floor. This cycle moves roughly 17 million cubic meters of water per second, more than 100 times the flow of the Amazon. And in doing so, it redistributes enormous amounts of heat across the northern hemisphere. Western Europe's climate runs on it. Without AMOC, London sits at the same latitude as parts of Labrador. Britain would be far colder, but the circulation's effects extend well beyond Europe. AMOC influences where the intertropical convergence zone, the band of intense rainfall near the equator, sits. It shapes precipitation patterns across the Americas and West Africa. It affects hurricane intensification rates in the Atlantic basin. It is a regulator, and regulators matter most when they are failing. The study published on April 14th, led by researchers analyzing deep ocean temperature and salinity fingerprints, found evidence that AMOC has weakened significantly over the past century, and that the rate of weakening may be accelerating beyond what the most widely used climate models projected. The mechanism is straightforward and alarming. Freshwater melt from Greenland and Arctic sea ice is diluting the salty surface water in the North Atlantic. Less salt means less density. Less density means the water does not sink as efficiently. If the water does not sink, the conveyor slows. A slower AMOC does not simply cool Europe. It reorganizes atmospheric circulation across the whole Atlantic basin. The intertropical convergence zone shifts southward. Moisture delivery to the eastern United States, particularly the southeast, changes. High-pressure anomalies over the subtropical Atlantic become more persistent because the heat gradients that normally drive their movement weaken. The Bermuda High, in other words, may not just be having a bad spring, it may be settling into a new normal. This is the part scientists are careful about because the link between AMOC weakening and specific regional drought events is still being worked out. The April study does not claim the current southeast drought is caused by AMOC slowdown. What it does is change the baseline. It raises the probability that the kind of atmospheric pattern driving this drought becomes more frequent and more persistent over the coming decades. That is a different claim and a harder one to dismiss. The last time AMOC disruption made major headlines was 2021, when a Nature climate change paper used sea surface temperature proxies to argue the circulation was already at its weakest point in over 1,000 years. That study was contested. Some researchers questioned the proxy methods. Others argued the signal was noisier than the paper suggested. The science remains genuinely unsettled on the exact rate of change, but the direction of change is not seriously in dispute. AMOC is weaker than it was. The question is how much weaker, how fast, and what that means for weather systems that hundreds of millions of people depend on. Back on the ground in the southeast, the immediate crisis is not abstract. Farmers are making planting decisions right now based on soil moisture readings that would have seemed impossible 3 months ago. Water utilities are modeling drawdown scenarios they were not expecting to run until summer. Fire crews are press-staging equipment in counties that rarely see significant wildfire. The drought is real, it is damaging, and it is not over. What the AMOC research adds to that picture is not panic, it is context. The Southeast has always had dry years. It has always had drought cycles. What changes if AMOC continues to weaken is the frequency floor. The baseline around which those cycles oscillate shifts drier, the extreme events sit higher on a raised platform, and the recovery periods between droughts shorten. The worst drought in 25 years starts to sound less like an outlier and more like a preview. The Bermuda High will eventually shift. Rain will return to Alabama and Georgia and Florida. The current drought will end the way all droughts end, not with an announcement, but with a series of ordinary storms that slowly refill what was taken. What will not reset is the ocean. Greenland is still melting. The North Atlantic is still freshening. And somewhere, 3,000 miles offshore, the conveyor that has kept this hemisphere's climate in a rough equilibrium for centuries is running a little slower than it did last year. Second, the deeper signal. What an ocean current running 3,000 miles away might have to do with rain falling or not falling on American soil. Start with the Bermuda High. It is a semi-permanent high-pressure system that sits over the western Atlantic, and it has been running unusually strong and unusually far west since late winter. High-pressure